Welcome back. So the last time we looked at limit and continuity laws, and we proved these laws. We also looked at how to apply them to prove that polynomials are continuous on all of Rn and rational functions are continuous wherever the denominators are not 0. In particular, linear maps are continuous. We saw that as well, right? This is the last theorem on continuity that I'll state, and then with all these theorems we have a powerful enough arsenal so that we can prove various things are continuous. So this is the theorem on composition. So So it's a long theorem to state, but all I'm saying is if I take two continuous functions and I compose them, then the composition is continuous. For example, before I prove it, for example, let's say let's say is continuous on all of R2. So why is this so, right? So the point is these things are polynomials. They are certainly continuous, right? They are continuous on all of R2. The images of these polynomials are some subsets of R2. Now sine and cos, some subsets of R, not R2. Sine and cos are defined on all of R. So this composition makes sense on all of R2. Sine and cosine are continuous on all of R, and this is a composition of two continuous functions. So these two are continuous. This is continuous because it's a polynomial, and since the components are continuous, this two variable function to R3 is continuous. Okay, this is how you would apply this. So it's very easy now to prove that fairly reasonable looking things are continuous. Notice that without these theorems, this would have been a formidable affair with deltas and epsilons. We don't have to bother with them anymore because of these theorems, at least in a variety of cases. You might have to bother with them in some cases, especially for piecewise defined functions. Caution. Be careful about piecewise defined functions. This is the case even in one variable calculus, right? If I give you a function which has different formulae for different values of x, then you have to be a bit careful. Right, so how does one prove this? We'll prove this and then we'll move on to differentiability. Yeah? Right, so how do you prove this? So what do we want? We want to show that this want whenever okay, this is what we want, and of course and x belongs to the domain of G. This is what we want. So in other words, we want this to be very close to this when x is close to A. What's the rough idea? We already know G of x is approximately G of A, and we know f of y is approximately f of G of A if x is close to A, if y is close to G of A. And we want to put all of this together and make it rigorous. Right. So how does one do this again? It's not at all difficult. So basically we use this first. Okay. So so in other words, if y is close to G of A, right, delta tilde close to G of A, and y is in the domain of f, then f of y is epsilon close to f of G of A, right? Now the point is if x is, let's say, delta 1 close to A, and x is in U, that is the domain of G, then G of x is delta tilde. G of x is then delta tilde close to G of A. Yeah. So which means that if you put these together, right, if x is delta 1 close to A, then G of x is delta tilde close to G of A, and hence f of G of x is epsilon close to f of G of A. Yeah. So your delta 1 is basically just equal to the delta. The delta that we want to choose is delta 1. Yeah. So this proves this composition law for continuous functions. It's also useful for it's also useful tool for computing limits of compositions of functions, right? Okay, so this sort of finishes our discussion of continuity. Now we'll do derivatives. So, all right, so how does one start? What is a derivative? In one variable calculus, a derivative tells you how fast a function changes, right? Like if you're going in a car, the derivative of your displacement tells you the velocity. Yeah. Now, what do we mean by how fast a multivariable function changes? Let's say we take a room, right? And if we look at the temperature in the room, it changes from point to point, right? Say, excuse my terrible drawing skills here. Suppose we take a room, the temperature varies from point to point. Now, what does it mean to see how fast the temperature is changing? What's a reasonable way to ask this question? So suppose, let's say you're a fly or a mosquito, right? Suppose you're at this point and you move slightly away to a nearby point, right? how much of a temperature change did you see? This is a reasonable question. So if you move in a certain direction away from this point, how much of a temperature change will you see? How fast does the temperature? So the question here is, how fast does the temperature when the answer to this question can and obviously will depend on the direction, right? I mean, let's say for the sake of argument, let's say this is facing outside. Let's say you have a window here, and let's say over here you have an air conditioner or something. I mean, of course, you shouldn't be opening the window and switching on the AC, but suppose you do it, and suppose it's very hot outside, say 40 degrees Celsius. Now, obviously, if you get closer to the window, if you go in that direction, you will see a temperature rising, whereas if you go towards the AC, you'll see the temperature falling. So the temperature will change at different rates depending on the direction, right? So to even make sense of this question, we must be allowed to move a little in all possible directions, right? That is, to make sense of this question, this point xyz must be an interior point of the domain. Now, of course, you can object saying that suppose it's not an interior point, then sure, you're allowed to move on, suppose it's a boundary point, suppose the domain is, let's say, a ball or something, let's say a disk in R2, and if you're here, then you can only move in these directions. So why don't we just restrict ourselves to moving only in these directions? That's a perfectly reasonable point of view, but it makes things far more complicated, right? So for this reason, in multivariable calculus, typically we talk of differentiability on an open set, when your domain is an open set, right? One can define differentiability, as we might later, on a closed set in a certain way, in that you consider some open set containing this closed set, and if there is a way to extend this function to the open set, then you can talk about differentiability on the closed set. But then on paper, different extensions can give you different derivatives and so on and so forth, right? So it's a slightly dicey affair. So for now, we will focus on interior points of the domain, right? Okay, right. So here's a definition. Given a scalar field, f from U in Rn to R, an interior point A in U, and a vector V in Rn, supposed to tell you the direction, f is said to be differentiable along V if this number exists. You move a little bit along V, meaning you take A plus H times V. So it's a one variable limit exists. So one variable limit, right? You can also view this, if you prefer, as d by dt at, let's say, t equals 0 of the one variable function f of a plus t times v. Okay, so this differentiable along a given vector is simply a one variable derivative, Okay, you move along that vector along a straight line and you'll get this. This is also called, this is given, it's given a fancy, it's given a fancy name. So you put this Greek letters nabla, so you say nabla f and you put the direction here at the point A. Okay. Right. If the norm of V is 1, this number is called the directional derivative of f along the direction A, along the direction V at the point A. Why do we want the norm of V to be 1? Because what is a direction after all? A direction is not merely a vector. I mean, even if you scale the vector by a non-zero number, you're still pointing in the same direction. Moreover, 0 is not really counted as a direction, right? That's why it makes sense to call it the directional derivative only when the norm of V is 1. But we will abuse notation and terminology and sometimes call this also the directional derivative along the direction V. Okay? But the hope is it's understood as to what I mean by the looking at the context, right? So this is the notion of this derivative along a vector or a directional derivative. So here are some examples. These are one variable limits, so they are very easy to compute. So if V is 0, then the directional derivative, let's say there's a scalar valued function, is obviously 0. This follows very easily from the definition, right? So let's do some more examples. So if f is linear, yeah, then what is the directional derivative? Then what is this? Or rather, not the directional derivative, let's say it's the derivative of f along A. This is the limit as h goes to 0 of f of A plus h times V divided by h, yeah? Which is of course equal to the limit as h goes to 0 of f of A plus h times f of V minus f of A divided by h. So these cancel out. So this is f of V itself. In other words, for a linear function, the directional derivative along a given direction or the derivative along a given vector is simply the function acting on the vector itself, right? Right. So this exists whenever this does and equals s times this. So if you scale the direction, the derivative scales, and indeed this is not very difficult. Suppose we take this one variable function, h of t, not s, and let's say g of t is h of s times t, right, which is f of A plus s times tv, right? Okay, so then how does one prove this? So this, by the chain rule, by the one variable chain rule, g dash 0 exists and equals h dash of s times 0 times the derivative of this, which is s, right? So which means that this exists and equals this times f. Okay. Right, so that's very easy. So let's move on. Okay. All right. So here we will now prove some sort of a mean value theorem. Right. So what is the one variable Lagrange's mean value theorem, if you prefer to call it that way? What is Lagrange's mean value theorem? Well, if f is differentiable, let's say it's differentiable on some open interval. This is not typically the statement, but okay, let's take the one that you're familiar with. Suppose it's differentiable on this open interval and it's continuous on this closed interval. Then g of b minus g of a is g dash of theta times b minus a for some theta in this interval, right? It can be derived using Rolle's theorem. So, or if it's easier to simply say it's differentiable on this interval, it's differentiable on a slightly larger interval, okay? Then it's, let's say, a minus epsilon, b plus epsilon. Then this is, as I said, in multivariable calculus we care more about differentiability on an open set, so might as well assume this hypothesis, right? Anyway, hypotheses aside, the point is this, right? So in other words, this is the dream, right? G of b minus g of a divided by b minus a ought to be the derivative, but it is the derivative, but at some unknown point in the interval. That's the only trouble. So there is an analog of that in multivariable calculus too. So assume that for all t in 0, 1, suppose it exists, right? Then we have this theorem. Oh, sorry, this is a scalar valued function. Okay, so this is the direct analog of this Lagrange's mean value theorem. Right. So how does this work? Let g of a, g of t be f of a plus tv. So by the one variable Lagrange's mean value theorem, by the one variable mean value theorem, g of 1 minus g of 0 is g dash of some theta times 1 minus 0. This is precisely this is precisely this, and this is precisely this. Okay, so it's very trivial. Okay, so it's not at all difficult to prove this. So let's move on. Right. Okay. So let's make one more definition. This is a definition that you may have seen in high school if you've done partial derivatives, but nonetheless. So when v is one of the standard directions, right? That is this one. This is the ith coordinate. Then if it exists, is denoted as xi of a, or sometimes merely as f subscript I of a, right. So, this is and called the partial derivative of f with respect to xi at a. Okay. Right. So, the point here is all known laws of nature are partial differential equations, meaning they are equations for partial derivatives of some functions. Even the most fancy laws like, but you may have heard of like quantum field theory, string theory, etc. The functions have weird domains and weird ranges, but nonetheless in some very generalized sense they are partial differential equations anyway, okay. More or less, okay. You can interpret them as so. Right. So partial derivatives are obviously very important. So a partial derivative is simply a usual one variable derivative where you keep one of the variables, all the other variables constant and just change one of the variables. Yeah. So here are examples of partial derivatives or directional derivatives existing. A polynomial has for all v and a in Rn. Why? Because what is this after all? This is simply a one variable derivative, remember? And one variable derivatives of polynomials surely exist, right? One variable derivatives of polynomials, I mean this is a basically this is a polynomial in T, and polynomials in T are obviously differentiable for all values of T, in particular T equals 0, right. If you have a bunch of one variable functions are differentiable as one variable functions, then if let us say g of x is the product of these one variable functions, for example sine of x, cos of y square and e raised to z, then the directional derivative of g exists for all v, okay, at any point where these are differentiable. Right. Now you can easily compute partial derivatives, can easily compute them because it's a one variable problem, compute them. For example, if you take the ideal gas law, right, this is a constant there, right, then this is partially differentiable in P, it's a polynomial after all, and it's also partially differentiable in P as well as V, okay, so it's easy to compute. A rational function is partially differentiable with respect to any xi whenever the denominator is not 0. Okay. Again, in fact, this exists as well for all v at such points. Again, just a small little technicality, when the denominator is not 0, the set of all such points is an open set. So it makes sense to talk about whether a function is differentiable over there or not, right? All right. Here is one more definition. If the partial derivatives with respect to all coordinates exist, then we get a vector valued function called the gradient of f. Okay, which is simply all these partial derivatives put together as a vector. Okay. All right, we are out of time, so we'll continue with the differentiability the next time. Thank you for joining.